Okay, so besides innovating on new ways to control an IoT device, another key research question in HCI is how do you leverage IoT devices to work together? We know IoT devices are connected, but do they really work together? Based on our current understanding, maybe the answer is no. Even though you already connect them, you interact with them one at a time, right? You have different apps for different IoT devices separately. But has it ever occurred to you that maybe these IoT devices, they can talk to each other? So rather than using Alexa to control the Nest thermostat, maybe there's more we can do to enable multiple devices beyond the Nest to talk to Alexa. So Alexa can have a better understanding of the environment. Basically, how do we go from controlling using A to control B, which is the current paradigm of IoT interaction. The key is that interacting with individual IoT devices alone should sum up to be smaller than the total of IoT's potential. And our goal is that if we do make IoT devices work together, we should be able to develop intelligence that is usually not possible when you have compared to you only interface with one IoT device at a time. So let's look at an example. So how can we make IoT devices inform each other to be more intelligent? The example here is I have a watch and a phone. And as you can see in this video, I can do some interesting interaction, having the phone to recognize the user's hand orientation or which part of the user's hand is touching the screen, whether it's pad, side of finger, or the knuckle. So it might seem this is really a new touchscreen, but in fact it's not. It's just a normal touchscreen. But what is different is that I have two pieces of devices. I'm actually looking at the watch orientation over here as the user's hand makes contact with the phone. And watch orientation correlates to different parts of the user's hand touching the phone. For example, if the watch is facing down, then it's very likely the user is using the knuckle, unless you wear the watch the other way around. So there's no new touchscreen invented, but by combining the phone and the watch, we're able to develop new intelligence that's previously not possible if we just use the phone and the watch separately. And the one functionality here is you can use knuckle to knock on the screen and then select text. So here's the research from Microsoft. I think some researchers like Microsoft, what they're trying to do is they have this Kinect camera, a depth sensing camera that can see the infrared image of the users and infer the depth, which is how far away the user is from the camera. And then they have a device held in your hand, maybe a phone, and they want to be able to correlate these two sources of signals. So let's see how they do that.
Simultaneously, dense optical flow is computed on the Kinect infrared image. Each 2D flow vector is converted to a 3D motion using the depth image.
So image can tell you
the 3D acceleration
the 2D movement
is estimated using a common filter
of the object. And if you have the depth dimension, you can do it in 3D.
Great.
And then you can, using this three-dimensional information, you can estimate the acceleration and velocity. And then you can look at the phone's accelerometer. And by correlating these two signals, you'll know which pixel is most likely to be the pixel of the phone, because those pixels are gonna exhibit the motion pattern that is the most similar in the phone compared to the rest, like the person, the couch, or the coffee table. So by being able to correlate these two signals, you can do a lot of interesting things like always knowing where the user's phone is, or you can, so we previously talked about the phone doesn't really know its absolute position. And using this system can compensate for the lack of knowledge. Another idea is called input retargeting. So here's the problem. You have multiple devices, but you probably have your preferred way of interacting with them, as opposed to having to learn the new interaction flow in each new device. You would hope that maybe I can just hold on to device A, and then I can retarget device A's input to any other device, like B or C or D. So basically, device A becomes your universal remote control. So even though you're interacting with the phone, you can still be able to control maybe the slide presentation or your TV or your thermostat. So all within one device. And the benefit is that, let's say you forget to bring your clicker, and without having to install a new app, you can pick up the phone and say, whatever I do on the screen of my phone is going to be translated or retargeted to the projector. So let's see how we can enable this kind of input retargeting. So here I am, I'm trying to control the slides. So the way we improvise this input retargeting is by demonstration. So first I demonstrate, I'm going to do this two-finger tap. And then I'm going to say correspondingly, I'm going to use this gesture to go to the next slide. And what happened in the back end is the system recognizes the connection between the two. And then using the recognition, gesture recognition on the phone to recognize the gesture on one device, and then retarget that information to a separate device. And there is a mechanism we develop so that we can translate this phone-based gesture to the mouse, simulated mouse events on your laptop in order to control what the user demonstrates should happen. And you can see there are a lot of different things you can do. You can just play with the system. You can do X on the phone and then do Y on the system. And the underlying layer would combine these two together to make the association. And because of time limit, I'm not going to go into a lot of details. If you're interested, ask more questions on Piazza. I can share the paper with you. So maybe another exciting challenge is to think about how we can make more physical things interactive. So in the previous two topics, we primarily talk about how can we invent new input devices, or how can we bring different IoTs data together to enable more intelligence. But the last challenge is quite different. You need to be creative. How can you make, for example, look at the things around you. How many of them are not IoT? And how can you make them IoT? So that's pretty much this challenge is about. Because we believe that eventually everything will become IoT. It's just a matter of time. So how can we go there? How can we bridge the gap? So there's a lot of research in HCI focused on adding these new sensing and actuation mechanisms onto everyday objects, turning the non-IoT things into IoT. So again, these projects are very creative, probably something you find very exciting and surprising. And I hope this can be also a source of inspiration for you to think about your project. How many of you have seen this before, Makey Makey?
Hi, I'm Jay.
And I'm Eric. We're graduate students at MIT Media Lab.
We have a dream that everyone is an inventor. So we created Makey Makey to let you invent just by alligator clipping. Alligator clips stuff like bananas to your Makey Makey. When you touch the banana, your computer just thinks you're touching the keyboard. The front has arrow keys, space bar, and mouse left click. When you're ready for more, flip the Makey Makey over and you've got more keyboard keys and support for the mouse. You can even use the board like an Arduino when you are ready. No programming, no breadboard. You don't even have to install software. Just plug it in USB.
Order your Makey Makey today and start changing how the world works.
Okay, so if that's not exciting enough, we have more. So this project tries to turn, again, similar idea.
Disney might be
anything
can become
a touch surface.
Developed a new technology that could put it in the company of Google Glasses and Apple computers. In a demonstration video, Disney Research turns everything from a doorknob and a table to a tub of water into a digital interface. The technology, called Touche, could perform simple computing tasks instead of a keyboard or touchscreen. Touche uses a sensing circuit to monitor changes in an electrical signal passing through an object when the object is touched by a conductive material. The technology recognizes the difference of touch by a single finger, two fingers, a grasping hand, and other gestures. Researchers believe with development, the technology could get rid of numbers and screens on mobile phones or music players, as users simply interface with their own body instead. Not Minority Report quite yet, but impressive gesture computing could be in our future. Just make sure you pick the right gestures, Disney.
Probably you started to see some patterns in these projects, and here's another example. Turning, again, static objects into something touch interactive. So this video doesn't have any audio because they want to demonstrate doesn't have any voiceover because it will demonstrate the acoustic aspect of the system. Okay, so one last example. So actually our next guest lecturer, Yang Zhang, is the author of this project. So you'll see, again, a new way for the same problem, turning everyday objects into touch-sensitive objects.
Smartphones, tablets, and kiosks. However, these technologies are too expensive to scale to large surfaces, such as walls and furniture, and are incompatible with objects having irregular and complex geometries, such as tools and toys. We present L03, a low-cost touch-sensing technique for large, irregular, and rapidly prototype objects. Adding touch interactivity to objects is easy. First, we add a conductive coating to an object. Then, we attach sensing electrodes to the periphery of the desired interactive area. An optional top coat can be applied. With this setup, L03 can detect different touch locations as well as enable coarse, continuous touch tracking. Our sensing principle works by injecting a small electric current into the conductive layer using a pair of electrodes. We then measure the voltage at all other adjacent electrode pairs. When a finger touches the surface, some current is shunted, causing a localized reduction in voltage. To better estimate the touch location, we rotate the current-emitting pair and repeat this process. This results in a mesh of cross-sectional measurements. Using tomographic reconstruction, we can create a 2D touch sensing image, revealing finger locations. Here is a real-world version of our illustrated setup, this time using 16 electrodes. The tomographic output is visualized on the laptop. We can apply standard computer vision blob tracking techniques to capture finger locations and movement.
So if we want to summarize what's the commonality among these projects, it's pretty much like this. You have some ordinary objects, non-connected, non-interactive. They need to supply some sort of input signals, whether it's acoustic or electricity. And then user will interact with these objects, which will disturb the signal that can travel through these objects, whether it's acoustic or electricity. And then you apply signal processing and machine learning methods to try to guess, associate the difference in the change of signal and the user's interaction pattern. And then try to kind of infer and guess what the user is doing that causes the changes in these signals. Okay, so that pretty much sums up the 3 exciting HCI questions about IoT. The questions you should ask yourself is, what would be your IoT project? Are you interested in any of these projects we've seen so far? Do you have any new ideas? Or are you interested in replicating any of these objects? So let me know and we can talk more.